This is Professor Kaushik Roy from Purdue University, and Kaushik has been doing fantastic work alongside Neuro-Inspired computing, and that's what we're going to learn about.
Right. Thanks. In this session, I'm going to talk about rethinking computing with neuro-inspired learning. I couldn't really come up with a better title, but anyway, we'll talk about it. We all know that deep learning has certainly made a huge amount of progress, right? And you open up any tech news or newspapers, you see deep learning all the time. Now, this is actually a little old, but I thought this is kind of interesting where AI won an art contest and the artists are furious. The human artists are furious. So what it really tells you is that it is really doing a great job in a lot of areas. However, the question, of course, is at what cost? So if I were to look at the biological systems, they, despite the tremendous progress that AI has made, some of these biological systems are extremely efficient. To that effect, actually, we had an IARPA project where the basic idea is, can I fly, and can I fly very effectively like a fly? So the flies do fly very fast and avoid obstacles, and they do all those with about 100,000 neurons or so. Turns out in our project we developed, actually collaborating with UPenn, they called it a flying monkey. The flying monkey certainly can't do the kind of things that a fly does. It's certainly not as agile. And it was taking about 1 to 2 watts of compute power, just the compute power. Whereas on the other side of it, if I were to really look at the fruit fly, the compute power is in the range of microwatts. And then if I were to look at going up the chain, mouse, dog, humans, it turns out there's a huge AI versus the natural intelligence gap. And the gap is really in terms of not certainly being able to do the kind of things that they do, but also the energy efficiency. And I know in the earlier sessions we talked about energy efficiency quite a bit, and that becomes a huge problem. Now, let's look at the energy cost of AI. And let's estimate the operational energy of AI chatbots. One of my colleagues, Anand Raghunathan, came up with these numbers, assuming that there are about 2 billion users. And if each user is using 5 queries per day and 365 days of the year, and if I were to look at the energy consumption, the power consumption of each query, that's about 0.001 to 0.01 kilowatt hours per query. Turns out the total is about 3.65 to about 36.5 terawatt hours, and correspondingly that's about 5 Hoover dams. So that's really, really huge. On the other side of it, if I were to really look at edge applications, and we did a case study on object recognition in a smart glass, and this is actually in an earlier technology, and where one can wear the glass and recognize, smart glass and recognize, for example, individuals. We did an analysis, and without going into the details of it, it turns out that under implementing a retina and a DNN on a smart glass, under ideal conditions, the battery life for this is not today's processor, a bit earlier processors, it turns out the battery life was about 1 hour or so. So if you now consider display power and all, it's probably going to be half an hour or so. So the question, of course, is we certainly have an existential proof that the brain is quite efficient. The biological brain is reasonably efficient. So where do these inefficiencies come from? First of all, the inefficiencies do come from the algorithms. We certainly don't know the algorithms of the brain, really. And the second thing that is also important to understand is the hardware architecture of the brain certainly is quite different from the standard von Neumann architecture. We don't really have a compute on one side and a memory on the other side. They're all mixed together in some interesting ways, and they do compute. We don't understand it quite well, but again, it is certainly not a von Neumann kind of architecture. And finally, the circuits and devices. I mean, we know that CMOS, being the workhorse of today's technology, certainly does really well. They're good switches. People can complain about the leakage and all, but they're reasonably good switches. But are they good from the point of view of implementing neurons and synapses? So to that effect, the question, of course, is, hey, is it possible that if I were to design a system, a neuromorphic or, for example, a cognitive hardware system, question, of course, is that you have to go all the way from sensing to really implementing these algorithms in the right kind of network architecture, implement them in a hardware, and finally, at the end of it, this hardware is going to consist of the right kind of circuits and devices. The question, of course, is, can I take some cues from the brain? And what are the cues that we can take? Can we look at the neuron model of the brain? Or, for example, whatever little that we know of the learning algorithms of the brain. The network topology. We don't understand a lot of details about the network topology, but people have done an extensive work, for example, in the visual cortex. Can I take some of those examples? And finally, at the end of it, the computing principles of the brain in some ways. And can I take some cues from there? And for example, I mean, if I were to really think about the neuron model, today we end up using, for example, in our deep neural networks, ReLU kind of neuron or a sigmoid kind of neuron and so on. The question, of course, is, should I use, for example, a integrate and fire neuron or a leaky integrate and fire neuron or the Hodgkin-Huxley model of the neuron or the stochastic neurons and so on. So what I'm really saying is that today's deep learning certainly is weakly inspired by the brain, but can I take some more cues and be able to do more efficient computations? How about the learning algorithms? I mean, today's learning algorithms is mainly backpropagation. And the question, of course, is, can I do, for example, local learning in some ways? Local learning combined with some global learning, can it give me fast and efficient way of learning? Can I learn with less data? That's another area that is going to be important. And again, when I look at the human eye, for example, we do foveation. We actually can focus on a particular object and you can ignore the clutter around it. So can I use, for example, learning of that type? So when I have rapid eye movement, which are the saccades along with, for example, foveation. And on the other side of it, the network topology, that turns out to be quite important. I mean, should it have long-range connections? Should it have feedback connections? What kind of connections are going to be good? And can I take some cues from the brain? And again, this is a difficult one. In one of the centers that we had, one of the jump centers, one of our collaborators was looking at the visual cortex and trying to figure out, hey, how good some of these networks that we use today are compared to what we sort of have in the brain. And on the other side of it, the computing principles, and that's what I'm going to be focusing on today mostly, is that what kind of compute should I have? Should compute and memory be integrated together in some interesting ways? Communication, that turns out to be quite important. Should it be event-driven computations? What kind of inputs are going to be important, right? And the inputs are going to come from the sensors. And so depending on the sensors, what kind of input should I use? Should I use analog inputs? Should I use, for example, DVS camera, which I'll just briefly talk about, and so on. All right. So now if I were to think about a cross-layer design, and the task that I might actually be looking at is, let's say, flying a drone, going from point A to point B, it has to avoid obstacles, right? It has to do, for example, first of all, what's called the optical flow, figure out what's around that drone using its eye, what objects are moving, what objects are stationary, and then based on that, I have to determine, hey, what path should I follow to go from A to B? And sometimes I have to also track objects. If they're moving objects, I have to track those objects and so on. Now, in order to do that, the first thing, let's say, that I'm going to be looking at is a completely vision-based navigation. And in such a completely vision-based navigation, I'm going to have camera as my input. And in this particular case, I can potentially have two different kinds of cameras. One is a standard frame-based camera that we're all familiar with. But more recently, there are more bioplausible cameras that people have been looking at, and the DVS camera. And I'll just briefly talk about some of these DVS camera. They provide slightly different kind of inputs. When there's a relative motion between the object and the camera, then you actually end up producing spikes. Now, once you have these inputs coming from the sensors, they need to be processed. And maybe the data that I get, I need to learn it. And I'll be learning it on different kinds of networks. And remember, I talked about the fact that, hey, can I use the neuron? And if I'm using, for example, the standard ReLU kind of neuron or the sigmoidal neuron, I might actually end up using, for example, a standard deep learning network. The question, of course, is, hey, is it possible that I should use some of this spike-based computation in it? Or maybe I should use, for example, a hybrid combination of spikes and the standard neural network. So the question is that what kind of neural network is going to be suitable? And finally, at the end of it, there's a need to think about how to implement some of these algorithms into my hardware. And so that's going to play an interesting role. And how should that hardware be? All right. So to that effect, I'm going to focus on that a little bit later. But going into the first, going into the sensors part of it, let's first try to look at what kind of sensors I can potentially use. And people for vision-based navigation, one way of looking at things is that I'm going to just use a frame-based camera. And for such a frame-based camera, one can certainly have these inputs going into, for example, a standard neural network. I'm calling it an analog neural network to distinguish it from a spiking neural network. But in reality, the implementations are all going to be in the digital mode. And then what happens is that if I were to do, for example, optical flow segmentations and so on, some of these cameras do have motion blur, and they don't have high dynamic range. On the other side of it, is it possible to have an event-based camera where if there's a relative motion between the camera and the object, I end up producing spikes. And if there's no motion between the object and the camera, then I don't produce any spikes. So with that in mind, and again, you can potentially have, depending on the directions I have, whether the pixel intensity is changing in the positive direction or the negative direction, I can potentially have spikes which are produced from this camera. Now, one interesting thing about it is that the timing between the spikes turn out to be quite important in this particular case. And if I were to use that timing information, then I probably should end up using a spiking neural network where it's going to be a leaky integrated kind of activation neuron. And such leaky integrated neuron can potentially capture the timing information. And using such timing information, potentially I can do, for example, optical flow depth estimations and so on. All right. So in other words, there could be potentially, it's useful to use different kinds of neural networks. So now let's try to look at, based on these inputs that I get from our sensors, what kind of algorithms or the network architecture that I should end up using. And to that effect, as I mentioned, that let's look at flying from point A to point B. And one of the things that is always important to do is to do optical flow. First of all, to figure out what's around me and what should the optical flow be like. And so what is optical flow? I mean, basically, you need to understand the surrounding environment and the motion around it. So you end up, for example, when you have the eye or the camera, you have to estimate the 3D motion vectors as 2D vectors on a retinal plane. Okay? And that's basically the optical flow, estimation of 2D motion field by computing spatial and temporal variation of the pixel intensities. And that's basically the front-end task that you do. And based on that, you can actually do various back-end operations. And so this is an example of an optical flow that I'm showing. Now, in order to implement that optical flow, depending on the kind of camera that you have, you can potentially have, for example, both the DVS and the frame cameras. One can implement that optical flow as a neural network. And it turns out that neural networks does pretty well when it comes to optical flows. And so this is an example of inputs that are coming in from a DVS camera. As I mentioned, things are moving, and based on those, I actually get positive or negative spikes, and the timing between the spikes are quite important to determine the optical flow. Now, this is just an example of implementing an spiking neural network-based optical flow, showing in this particular case, in order to have a good endpoint error, we were using in this particular case about 13 million parameters. Now, on the other side of it, to effectively or to do a better job of optical flow, turns out one can actually use a combination of spiking and a standard neural network. And now in this particular case, I'm not only using both the DVS camera and the frame camera together, but I'm combining that information together in that neural network that I'm showing there. And it turns out that just because I'm able to actually take the best of both worlds in this particular case, I'm able to actually get good endpoint error, but with just about 7.5 million parameters. And where I'm utilizing a hybrid neural network. Now, one can certainly go a little bit further and say, hey, can I really come up with very low, lightweight architecture at the edge, which could be suitable for edge applications with about 60,000 parameters in this particular case I'm showing it. Turns out it's possible. You're going to get some errors, extra errors that are going to come in, but with about 60,000 parameters, it turns out it's possible to do reasonable job of optical flow. But in this particular case, the network is a completely spiking network. And the reason why spiking networks in this particular case is better than a standard neural network is because of the fact that I can capture basically the timing information. Just because I have leaky integrate and fire neurons and I'm able to store my values of the membrane potential over time, then I can actually do better sequential operations. Yes?
You're only using event cameras here?
In this particular case, in the bottom case, yes. All right. Now, a few other things which are kind of interesting is that when it comes to these DVS cameras, in fact, it turns out object detection and tracking is also kind of easier in some ways. Just because I'm looking at the relative motion, object detection and tracking not only becomes easier, and in a lot of cases, I'm also able to figure out what speed the object is going at. And leak actually plays a very, very interesting role in that. So to that effect, one of the other things that I just wanted to briefly mention that, for example, if you have a camera and the ground truth is that this particular vehicle is moving, it turns out what one can potentially do is using one layer, in this particular case, just a layer of spiking neural network. And you have to train the neural network for not only the threshold, but also the leak part of it. If you're able to do that, you can actually able to guess the speed or at least determine the speed. You can speed beam basically as to like what speed the car is moving at. And that's something that you can train, and that's what we used, showing in this particular case an example of a, let me see, an example of a ring that I'm showing here, and the ring is moving at a particular speed across from left to the right. And this is the drone. The drone is supposed to actually estimate the speed of the object that is moving, and then based on that, go through the ring. Now, the DVS camera is right here. The reason why the DVS camera is shown separate from the drone is because of the fact that the camera weight is actually pretty high, heavy, and it's not going to fit into that small drone. But anyway, the thing is that using such spike-based computation units, which are hybrid units that I'm talking about, not just fully spiking, but a hybrid combination of both spiking and non-spiking networks, what one can do is one can actually implement efficiently some of these algorithms where you can not only estimate the speed, do optical flow, and then make a decision based on what you need to do. All right. Now, the reason I talked about some of these algorithms is because when you try to implement some of these algorithms in an edge hardware, not only you need to focus on the standard deep learning, in some of these cases, depending on the kind of sensors that you have, some of these other kinds of neural network also becomes important. Whether it's a leaky integrate and fire kind of neuron, or a standard ReLU neuron, or a sigmoid kind of neuron, and so on. So believe that the hybrid combinations of some of these are actually quite suitable for edge applications for energy efficiency and so on. Now, if I were to look at, for example, the hardware part of it, let's focus on the hardware part of it. And if we were to implement some of these in an energy-efficient hardware, what are the requirements? At the end of it, as we know, the hardware fabrics, if I were to look at, for example, speech, language, vision, all these applications, your main operations, and this is a chart from IBM, the main operations that you end up doing are shown in red, which is basically the matrix vector multiplication operations, or matrix-matrix multiplication operations, and that's the main computation that you end up doing. Now, when it comes to, for example, today's transformers, and language models, a few other things which are also important. Turns out there's a attention block plays an important role. Not only I do matrix-matrix multiplication there, but at the end of it, I also do a large number of softmax operations. And so softmax operation turns out are also quite important. And that really means, in some of the other networks also, you need to do, for example, tan hyperbolic or sigmoid kind of functions. And each of those require exponential operations. So the question, of course, is that, hey, can I also accelerate some of these other operations? Not only the matrix vector multiplication operations, but also the softmax and other kinds of transcendental operations, if I can make it faster.
What precision are you doing all this in?
Some of those are going to be in, for example, integer, if I'm looking at some of the compute in memory, though it can also do, for example, floating point operations. But mostly some of these can be done in int 8 or 4. Now, the hardware fabrics that we certainly would love to look at is the circuits and architecture that can efficiently implement some of these algorithms. So to that effect, one problem that in the morning we heard about it is that there's a need to really think about reducing the or at least alleviating the memory wall that exists today. So if I were to really go and fetch objects from the memory, do the computation and bring it back to the memory again, that's inefficient. Is it possible that I do my computations mostly near the memory or in the memory itself in some ways? There are other possibilities. Certainly, we can do approximate and stochastic hardware. Now, approximations we certainly end up doing, no question about it. There's a lot of quantization that needs to be done, and quantization is certainly approximations, and but other kinds of approximations can also be done. Then, of course, at the end of it, to also think about the devices. Should I use CMOS? And we all know that CMOS is extremely difficult to replace, but are there any other devices that can potentially give me some advantages in the near future? Yeah. The stochastic hardware, I'm talking about neurons which are has a stochastic switching behavior. And one can do such, for example, if you have a sigmoidal switching, if the switching is a stochastic sigmoidal switching, I can implement that in, using some of these interesting devices. For example, a magnetic tunnel junction can potentially be utilized to do that stochastic sigmoidal switching. So where are we today? Today we are certainly in the multi-core GPUs and accelerator domains. The question, of course, is it possible to do some of these compute in memory techniques or approximate and stochastic hardwares to or improve the energy efficiency? All right. And this is basically, when I try to implement some of these algorithms, there are certainly lots of inefficiencies with current GPUs, CPUs, and TPUs because of the memory wall, as I mentioned earlier. And if I were to plot, for example, in this particular case, where I'm plotting the hardware flops over the years versus DRAM bandwidth and the interconnect bandwidth, they're not scaling as fast as, for example, the compute. And the gap is large, and hence, is it possible to actually reduce that gap by, for some of these computations that we talked about, the matrix vector multiplication, or for example, softmax and others, by using, for example, rather than a von Neumann architecture, which is sort of bottlenecked by the memory bandwidth, is it possible to use, for example, some sort of compute near or in memory? And so the solution could be potentially NVM, which is non-volatile memory, or it could be, in fact, even CMOS. Can I really have compute in memory? Crossbar-based solutions for compute in memory. Now, what do I really mean by compute in memory? If I were to really think about a standard memory, let's say, which I'm showing here with the word lines in the horizontal direction and the bit lines in the vertical directions, my standard memory, I turn on one word line, right? And then I read and write into my memory by turning on one word line. However, it turns out that if I were to turn on multiple word lines, and I may or may not be able to do that in all memory, right? For example, in a 60 cell, I may not be able to simultaneously turn on two word lines. But if I'm able to modify my memory and turn on two word lines, it turns out in some of these cases I'll be able to do, by changing these peripheral operations to a certain extent, I will be able to do, for example, AND operations, OR operations, or XOR operations. Now, I can go a little bit, and those would be what's called digital compute in memory. Now, if I were to then do, for example, turn on multiple word lines, then I potentially can do, for example, matrix, dot product operations on my columns, but those are going to be in the analog domain. And since I'll be doing it in the analog domain, there's a need for some sort of an analog to digital converters right here. And they can be done using SRAMs, non-volatile memories, and so on. Now, this is an example of analog CIM that one can potentially use. And in an analog CIM, what happens is that I have these matrix vector multiplication units that I just showed. You have an input, which is a DAC that comes, and output of that crossbar has some ADCs. And as you can see, you need multiple ADCs to do the computations. And we'll see the bottleneck would turn out to be the ADC. And then along with that, I mean, for example, each core can potentially have an ADCs, these crossbars, and a multiple of such crossbars, register files, ALUs, and some memory. And that could be CMOS memory. And each of those could be tiles, and you can repeat some of these tiles together to form a larger number of tiles to form, for example, a spatial kind of architecture, which could be network on a chip kind of architecture. Now, let's say that I want to do, for example, a matrix, vector matrix multiplication. And so I have activation, let's say, which are in 4 bits. The weights, let's say, are also in 4 bits. Now, what I would like to do then is that if I were to do these computations into my matrix vector multiplication units, which are MPMUs, and let's say that I'm using, RRAMs, could be SRAMs, or could be, magnetic devices, magnetic tunnel junctions. In those cases, what I'm going to do is I'm going to take this data, or the weights, and I'm putting those weights into as bit slices into my 2 MVMUs in this particular case. Now, if your MVMU implements basically 1 bit, then you need 4 such MVMU units. If you can implement directly those 4 bits in one memory array, then of course you can do it with one. But there are several issues when you try to do that for reading. And similarly, on the other side of it, if I were to look at the inputs, I'd like to do it as, again, bit streams. And so at the end of it, what I'm going to have is my matrix vector multiplication unit in this particular case is going to have a bit stream coming in. And then I also did the bit slices. So at the end of it, when I'm going to get my computations, I have to accumulate all the results together. And that's how I'm going to do my computations. All right. Now, there's several challenges to that. And the challenges are, just to talk about a few, there are several non-ideality effects. So what are these non-ideal effects? There's going to be parasitic resistances on these lines. And depending on the device that you're using, depending on the device resistance that you have, and whether the devices have nonlinearities, you're going to have problems. So these non-ideal effects are going to give you non-ideal current, and that can potentially cause problems. The second thing that is also important to understand is that the ADCs, we're talking about analog to digital converters, and these analog to digital converters are required at each and every column. And think about it, if you have a 64 by 64 crossbar array, then you need, or a 128 cross 128, you need about 7 bits. And you can't even have so many of those ADCs, so you have to multiplex those ADCs, otherwise you're going to have problems. And the cost of the ADCs and the area is going to be also dominated by the ADC cost. All right. Now, CIMs, all the compute in memory that we're talking about, have certainly limited functionality. And the limited functionality is really related to the fact that I'm doing mostly matrix vector multiplication. And there are other operations that I need to do. And if I need to do those other operations, is it possible that I can actually do something about it? And finally, at the end of it, this may or may not relate to the NVM technology. Poor scalability of these devices in some of these deeply scaled technologies can potentially be an issue that one needs to think about. All right. So what are the potential mitigation approaches for the non-ideal effects? There's a need to think about some sort of a cross-layer optimizations. Devices, bit cells, and peripheral circuitries need to be considered all simultaneously. The ADC overhead is a problem. So is it possible that I can get rid of the ADC completely? That's another possibility. So how do I get rid of the ADCs? Rather than using, for example, a 7-bit ADC or a 6-bit ADC, is it possible that I'm going to use 4-bit ADCs or 3-bit ADCs? Or, for example, just to get rid of the ADC completely. But that would require, for example, training. And the training would require it to understand the quantization that is done for removal of that ADC. Okay? And so not only you learn the data, but at the same time, you need to learn basically your hardware. A limited functionality to that effect, is it possible that I take this matrix vector multiplication unit to the crossbars, and is it possible to embed more functionality into those crossbars? And it turns out that in some cases, actually, you can embed, in some ways, a ROM, a read-only memory, into that RAM at possibly no extra cost, no extra array cost. So in other words, if I'm able to actually implement, for example, an exponential function of the math table into that crossbar array, while still being able to do the matrix vector multiplication operations, or, for example, the RAM operations that I do, that could be interesting. And
So you mean use a lookup table?
yes, okay. Yeah, use a lookup table. And the lookup table is going to be built into, if I'm able to build that into my array itself, then I don't pay extra area for it. And of course, can I look at, for example, non-volatility? But then again, when we look at non-volatility, there's a need to think about high endurance, high density, and so on. All right. So to that effect, certainly there's been a good amount of work which is going on, and I'm showing here are all kinds of, I call it neuromimetic devices, and they are both colorful, literally and figuratively, and some of these devices could be potentially useful, but some of those are not very mature. But there are a few devices which are, have reasonable maturity. For example, RRAMs, PCMs, or STT kind of devices. And the question, of course, is can some of these devices be, be useful in implementing some of these crossbar arrays? Now, just to very quickly analyze, PCMs, RRAMs, and magnetic devices versus CMOS, what is really important in this particular case to look at is the fact that the cell area, and that should not really compare with CMOS. CMOS is certainly a lot more scalable. Difficult to, for example, scale a magnetic device beyond a certain limit, because the size of the MTJ plays a very, very important role. And it turns out that the volume of the magnet basically determines the barrier height that you can have. So when you scale your devices, that plays a big role. The barrier height, if you want to keep it at 40 KT or so, scaling it down to a 10 nanometer magnet becomes quite difficult. So those are the things that one has to look at. But at ISO technology node, it turns out that these certainly have good cell areas, but write energy, write latency are actually pretty bad for PCMs and RRAMs. And more importantly, actually the endurance of these PCMs and RRAM devices are actually quite small. So to that effect, it's difficult to use them really certainly for training applications and all. MTJs certainly are better, but certainly have several other issues because the R onto RF ratio of magnetic devices are actually low. All right, so now going a little bit further into the crossbars. So I'm basically looking at a crossbar which looks somewhat like this, where I have a bunch of inputs which are coming in, and then I have a conductance associated with each of those devices. And at the end of it, what I get at the output is a summation of VI times GI, and that's basically my dot product. If I turn on two word lines, as I mentioned earlier, people talk about that, and they say, hey, by adding some circuitry in there, I can do digital computation. It could be XORs or adders and so on. All right, so what kind of devices that I can have in here? I can have PCMs, RRAMs, STT devices, or in fact even CMOS. And we'll see that one can implement some of those quite effectively in 8T cells. All right, so a few other things that this is a bare-bone crossbar, but I certainly need my access devices and a bunch of other interface circuitry for these analog to digital converters. Now, there are possibilities of getting rid of that access device. There's been a good amount of work which is going on, and for example, using ferroelectric capacitors, but each has its own kind of problem, but potentially I can get rid of that access device. And now, as I mentioned earlier, that your peripherals are going to be one of the major bottlenecks that one has to look at. Here you have this sample and hold and analog to digital converters. So now if I were to take each of those MVM units and put them together and connect them through sort of a network on a chip, then I can potentially implement a spatial kind of architecture. This is not showing all the details, but one can potentially think of an architecture which looks like this. And certainly along with that, you can have a high density of chip memory. So, but as I mentioned earlier, that you're going to be dominated now by your ADC cost. So now if I were to go into a little more details of it for this architecture, turns out that each of those, I can potentially think of a spatial architecture somewhat like this, where each of those cores here is implementing, for example, a crossbar. And along with that, it has also some other logic around it, so a little memory. And each of those cores put together can be connected through a shared memory and some first-in, first-out buffers and so on to form a tile. And each of those tiles can be now put together on a network on a chip kind of an architecture. So that's a spatial architecture one can potentially think of. Now, if I were to do large-scale matrix multiplication, then it turns out that I may not be able to use, for example, 1,000 cross 1,000 crossbar. There are issues that's going to come up in terms of, for example, non-idealities, effect of using, for example, the ADCs. So you have to break up your crossbars into smaller crossbars, and then you have to accumulate the results. And as I mentioned earlier too, that you need to do, for example, in order to actually reduce the cost of the ADCs and to do for example, what you have to do is bit slicing, which is weights and inputs together, so that weight slicing and input streaming would enable you to do low precision crossbars and low precision DACs to compose high precision NVMe units. Remember, of course, you have to do, for example, accumulation of the results. All right. As I mentioned earlier, the challenges were the ADC cost and the non-ideality effects. And the non-ideality effects can lead to, for example, having difficult to do larger crossbars. The larger the crossbar I make it, then more of these non-ideal effects are going to come into picture. And that's going to cause problems. So to that effect, now let's look at, can I really implement crossbars or compute within the SRAM array using, for example, in-memory Boolean computations in CMOS static random access memories. So one can think of, and again, it's a little difficult to read, I understand, but these are all 8T cells that I'm showing here. Okay? So the 6T is really for the write operations. There are 2 extra transistors, which are really for doing the read operations, so separating out the read and the write terminals. In this particular case, what I can now do is I can read, I can turn on, let's say, 2 of the word lines, the read word lines, and by having some extra circuitry right here, the sensing circuitry proper, I can actually do AND operations, OR operations, and all. Now I can do a little bit better and say, hey, I'm going to turn on some of these word lines and have some extra circuitry right here to do, for example, add operations. And not only I can do add operations, since write and read are decoupled in an 8T cell, I can turn on the write word line, in this particular case, to be able to simultaneously write into the cell. So I can do that. And so in other words, what I'm really doing in this particular case is a digital compute in memory. And rather than having a standard conventional instructions of 2 loads, add, and a store, I'm replacing that with, let's say, a compute in memory add operation, if I can. Now, going further, by turning on in an 8T cell multiple read word lines and pre-charging the bit lines, I can potentially also do some of these matrix vector multiplication operations. So this is basically, again, using, for example, showing the read part of the cell, which is the 2 transistors which are shown there. The 6T is for the write operations. So what I can now do is I can turn on multiple read word lines, and based on how much I discharge, I can potentially figure out, hey, my matrix, or rather dot product operations. But I certainly need, in this particular case, an ADC. And it turns out that, as I mentioned, ADC cost is going to be the bottleneck. So is it possible that I can use low complexity ADCs? Can I use sparsity in some cases? For example, there's a lot of inputs which are zeros, and if I can figure out, if my 50% of the inputs are zeros, or 80% of my inputs are zeros, then I can potentially actually have lower complexity ADCs. So to that effect, one can certainly think of an adaptive, sparsity-aware CIM score, which can potentially figure out, hey, is it possible that I can do figure out how many zeros I have in my computations, and based on that, I can come up with the right kind of ADC complexity and use that ADC for my computations. And if I do that, certainly I can get reasonable results, but you're still dominated by the red thing that I'm showing here is basically the ADC cost. And that's still basically the problem. So the next question, of course, is that can I mitigate the ADC cost? And one way of mitigating the ADC cost is to say that, hey, can I get rid of the ADC completely? To that effect, is it possible to do some sort of a partial sum quantization? We've been talking about these partial sums, right? Summation of VI times GI. All those partial sums that I have, is it possible that I quantize them? And if I quantize them, what's going to happen? Can I get something interesting? So to that effect, rather than basically thinking about when I have a crossbar, I had a mux and these ADCs. And can I reduce the complexity of ADC and make the ADC to be maybe 1 bit or 1.5 bits and so on? Now, if I do that, if I quantize my partial sums and make my ADCs to be, ADC precision going from, let's say, 6 bits to 1 bit, what I find is that my accuracy suffers terribly. In fact, in reality, if I really look at for example, 1 bit or 1.5 bit, I basically have random outputs. So can anything be done about it? So one possible solution is that you can train the DNN model with partial sum quantization, and you put it in the training loop. So in this particular case, you're not only learning the data, but you're also learning the hardware in some ways. So you basically train the model with partial sum quantization, and when partial sum is quantized to binary, and in this particular case +1 and -1, then you potentially get an ADC-less CIM. Okay? Now there's a catch to it. You can't do it directly. You need some scale factors. And these scale factors are going to be important, and these scale factors are full precision scale factors. Okay? So you have to multiply them with the scale factors. Now, depending on the type of design that you do, you can potentially have scale factors per column or scale factors per array, and so on. If it's scale factor per column, then of course there'll be a large number of scale factors, and you have to do a large number of multiplications and so on. Now going further, you say, okay, can I do slightly better if I were to think about not binary, but ternary? And in this particular case, I have 1, 0, and -1. And assuming that I know that there are a good number of zeros, if I can utilize that later on. And now again, in this particular case, you certainly need your scale factors, and the scale factors are going to play an important role. So now what happens is that, remember I showed that if I just arbitrarily reduce my precision from 6 to 1 bit without basically putting in the training loop, I had my accuracy suffered. But now with putting it in this case training loop and having those proper scale factors, as you can see for this ResNet 20 CFAR 10, you can potentially get back most of your accuracy. And few other things which are also important is the fact that looking at the scale factors, you can do per bit slice scale factor, or per column, per channel, or per layer. And of course, I would like to do per channel or per layer, but of course that reduces my accuracy to a certain extent. But I do need scale factors, and the granularity of the scale factors that I have is going to play an important role in determining what kind of accuracy I get. So scale factors are going to be crucial in ultra-low precision quantization. So now, if I were to think about deploying this ADC-less compute in memory accelerator, in that case, this part of the crossbar array, I'm using, for example, let's say I'm using 1 bit, and so I can now basically have all sense amplifiers instead of ADC, or in fact, in this particular case, it's a 1-bit ADC. And then, of course, I need scale factors. So what the computations that I need is basically now then, I have the scale factor memory, and I need to then multiply the scale factors with this partial sum quantization that I have, right? I keep on doing that and accumulate the results as shown there, and that's to get my final result, which requires, again, in this particular case, a floating point multiplier and adder. Okay. All right, few other things that is important to note is the fact that when I have a large number of these scale factors, the scale factors would require high data movement and energy also. Right? Is it possible that I can actually reduce my scale factors? And also another thing that I note here is the fact that if I look at, for example, the ResNet that we're looking at, layer 10, 11, layer 12, and so on, it turns out that the scale factor access energy is plotted here, that a good number of accesses are going to be for the scale factors that I have from my memory. And that's going to cause, again, another bottleneck. So is it possible that I take care of these scale factors by, and the second thing that I also notice is that for each of those layers, not only the scale factor access energy is important, but a few things which are kind of interesting to note is that the number of zeros per layer is really high. The values which are 1 and -1 are much lower than really the number of zeros, and I have a huge number of zeros. So if I'm having a huge number of zeros, is it possible that I can take advantage of it and take care of it in the computations? So what's the solution then? One possible solution could be a two-stage quantization. The first stage is basically having that analog CIM crossbars that I talked about. So the first stage quantization is using these scale factors to quantize my partial sums. And based on that quantization, then I do stage 2 quantization of these scale factors now. So I can potentially think of having 4-bit scale factors with a scale factor here, which requires a floating point multiplication, but that's much, much smaller. So if I now implement that in a circuit, so what I have now is a hybrid kind of computing memory, where this part of it is really implemented as an analog crossbar, and the scale factor multiplication part is basically going to be a digital CIM. Okay? So if I do this digital CIM along with this multiplication and a few other things which are required, which I'm not showing here, that you need to now not only add, but you have to be able to subtract because you have 1, 0, minus 1. If you do that and take care of the large number of zeros by not multiplying with zeros, you can potentially get a good amount of improvement. And showing here that accuracy results on a CFAR 10 for different kinds of ResNets. This is the regular ResNet and the wide ResNet, showing that with the ADC precision down to about 1 or 1.5 bits, you can actually maintain more or less the accuracy that you'd like to have. I'm going to skip this and, all right. So that's with the CMOS part of it. Now, let me see how much time I have. All right. Now, certainly, when it comes to these non-volatile memories, as I mentioned earlier, there are several things that you potentially need to do. And if I were to use, for example, rather than CMOS, an SOT, a spin orbit torque-based magnetic tunnel junction, one certainly has to use sparsity, but it turns out the devices need to be co-designed along with the system that you're designing. So what do I really mean by that? I'll just talk about in a minute. But the reason why we might have to do that is because of the fact that if I were to look at the characteristics of some of these RRAMs, PCMs, and STT devices, the RRAMs can potentially be multi-bit. STTs are single bit. But STTs are good in terms of endurance. Endurance is high. And write energy is also low compared to, for example, RRAMs. But compared to CMOS, they're still 5 to 10x higher. But more importantly, there's not much of a conductance drift, which you see that in the RRAMs. So can I take advantage of it? But the problem with the STT devices or SOT devices is the fact that R on to R off ratio is actually pretty bad. Okay? So we're talking about TMR of the order of about 150, maximum 200 or so. The ones that we've been looking at working with IMEC is of that order. All right. So one now can potentially do a device circuit co-design flow. And without going into all the details of it, that if you were to design a crossbar, it turns out it's very difficult to turn on multiple word lines in an analog crossbar because of the fact that the on to off ratio is low. The parasitics of these wire lines are going to be large enough to actually offset some of these advantages that we'd otherwise have. R on to R off being low, that's a problem, and you can't turn on too many word lines. But now if you can optimize your devices to a certain extent, along with looking at algorithmic sparsity, sparsity lets you actually turn on more word lines. Turns out you can actually reduce the computational error, but what is the device optimization that one can potentially think of? That's basically when I'm utilizing my SOT device, spin orbit torque device. The writing is done, if you're familiar with the SOT devices, the writing is done using the heavy metal. Okay? and you don't go directly through the magnetic tunnel junction, the oxide. Now, if I can make my oxide slightly thicker, and if I make my oxide thicker, what happens is my read suffers slightly, but my TMR increases. And then I can potentially use a larger TMR to make my crossbars. So using such approaches of device sort of circuit co-design or system technology co-design as they call it, you can potentially now have slightly larger crossbars. Still difficult to do, but can potentially have slightly larger crossbars. How about RRAMs? I feel RRAMs are going to be problematic because of the drift, and it's certainly possible to use it probably for inference applications, but for training, RRAMs are certainly problematic. So one way of taking care of RRAMs in, for example, training, can potentially be that using the fact that SRAMs are compute accurate, trainable due to high endurance, the cons potentially slow and inefficient due to high off-chip data movements and all. Is it possible that I can use higher density RRAMs, but in that case, for training applications, I have to do some sort of a transfer learning, meaning thereby that the first few layers of the network, let's say, are going to be implemented using RRAM as a training architecture, and they are transfer learned, meaning thereby I'm not going to be writing on those, right? I'm only going to be writing when it comes to, I'm only going to be writing into the later layer SRAM blocks. Okay? So when I do backpropagate, okay, I backpropagate only up to the CMOS layers, update the CMOS layers, but when we forward propagate, I forward propagate all the way through the RRAM layers. But I don't update the RRAM layers. And there's been transfer learned. And hence, one can now use it because if you're not writing too much, you can potentially actually have better reliability of those RRAMs. Now, quickly going into the next set of things, I talked about the fact that, hey, can I do beyond NVM computations? One possibility is to embed transcendental functions to on-chip memories. And it's possible to do that in RRAMs, STT devices, and in fact, even SRAMs. It's possible to do that in SRAMs, but it's possible to now, for example, embed a ROM into a RAM and to be able to do multiple kind of operations. So let's try to look at an example with an NVM technology, because it's easier to see the NVM technology. If it's CMOS, you lose the value, so you have to actually rewrite the value, so it takes a little more effort. Now, so this is a ROM overlaying RAM. The basic idea is that I still have this sort of a word line, source line, and bit line architecture where I have this magnetic device in this particular case. It doesn't have to be, it could be an RRAM, but it's more suitable for magnetic devices. I have an access transistor and so on. So the only difference that you see is that rather than having one bit line, I actually end up having 2 bit lines in this particular case. So, and each of those cells are either connected to bit line 0 or bit line 1, but not to both. If and the ROM connection, the ROM storage is based on where if it's connected to bit line 0 or bit line 1. So to that effect, if I were to think about what I've stored for the RAM data, in this particular case, RAM data is stored, I'm showing here is 1 to be parallel combination and 0 to be anti-parallel combination. So based on the connections that I have, or the configurations of the MTJ that I have, the RAM data is either 1 or 0 as shown there. Okay? 0 or anti-parallel, parallel is 1 in this particular case. Now, on the other side of it, if I were to think about the ROM data that I've stored is based on where the connections are made. If I've connected to the bit line, then bit line 1, it is 1. If I've connected to bit line 0, it is then 0 that is stored there. Okay? So basically, in other words, if I were to have 1 MB RAM, I can potentially have 1 MB ROM. stored in there. Now, how much extra do I pay in terms of the array area? It turns out I have enough space to route that line, and hence I do not pay anything extra from the array area, but I do have slight changes in my sense amplifiers. So now if I were to really think about the RAM operation, the standard RAM operation, how do I do it? I activate both my bit lines. Okay? And if I activate both my bit lines, and if I turn on one of the word lines for the standard operations, on one of the word lines, I can do my RAM operation, whether it's read or write into the RAM. That means I'm writing into the magnetic tunnel junction or reading from the magnetic tunnel junction. And basically with that sense amplifiers that I have. Now, what about ROM operation? If I want to retrieve my ROM data, so what I do is I turn on my bit line, and let's say in this particular case I'm actually activating one bit line, and in this particular case the bit line 0. Okay? And then I have my word line activated. So what am I reading from that row? From that row, what I'm really reading is I have either a connection to this bit line or no connections in these two cases. So if I don't have a connection, my resistance that I see is very high, infinite resistance. If I actually have a connection, which can be RP or RAP, then I see some resistance. And by looking at that and by sensing that, I can actually determine my ROM storage rather. And how do I do this? My NVM operations, I can turn on multiple word lines. In this particular case, I'm turning on 2 word lines and doing digital NVM operations. And then I can potentially have my sensing circuitry to do my other operations. Could be, for example, digital operations or matrix vector multiplication operations. So now, why is it interesting? The interesting thing is that I can potentially store my math tables now in the ROM itself, in my on-chip memory itself. So all these exponential functions that we talked about to do sigmoid, tan hyperbolic, or for that matter, softmax, which are important for example, LSTM, BERTs, or GPTs that we looked at, it turns out you can do that more efficiently. So you can do some of your computations, for example, in a attention unit to QK transpose softmax V. That softmax can be effectively done using the values stored in your ROM. And what kind of speed up that you get? It turns out compared to the GPU A40, and A40 of course is implemented in real life, but this is actually simulation results, shows about 3 to 30x of improvement in terms of energy efficiency. Now, I know that we don't have much time, but it's also possible. We talked about the fact that doing some of these computations in the L1 cache register files or L2 cache, but it's certainly possible to do some of these computations in DRAM. And in a lot of cases, that makes sense to do in some cases for some applications. For example, I can do majority-based vector operations. This is basically if I can turn on multiple of these word lines, multiple lines. I can do, C out is basically the majority of A, B, and C in, and sum is the majority of A, B, C in, and 2 C outs. So to that effect, one can potentially think of data stored in the DRAM to be somewhat like this. You have these data stored in blues, and where I'm going to have data of A and B stored here, and the sum of A and B are going to be stored there. So what I can potentially do as an example is that I can take my A's from there, rewrite in a particular section of the memory right here, A's and B's, C's, C in, C out, and these are written there. And then what I can potentially do is take this red part of the array that I'm showing there. And if you can do multiple row activations, then you can potentially, by changing the sense amplifiers, you can do majority operations. And by enabling these 5 word lines in this particular case, and then enabling the sense amplifier, that can potentially give you that majority operation. And similarly, you can also do, for example, with some modifications, calculate C out and C in, and based on the C ins, A, B, C ins, you can also calculate C out by, again, turning on 3 word lines in this particular case.
Is that majority operation like an analog operation?
Yeah.
So the analog sensors just sort of see how strong
Right. So to that effect, actually, we did an analysis of it in a case study of doing sort of a K closest nearest neighbor accelerations, where we looked at a host processor which is going to do top K sorts, and then you have an in DRAM computing for Manhattan distance computation in this particular case. And what we did is we did a simulation and compared to, for example, a baseline which didn't have the computing memory, and that sort of showed about 11x improvement in performance if I were to do that, if I can divide the computations that way. I guess I don't have time, so I'm going to stop here. Probably have to stop anyway because I'm having problems here now. All right, so the last couple of slides that I had was really that going forward, we talked about compute in memory, but one has to really think about where to compute in memory. Should it be in register files, L1 cache, L2 cache, DRAMs? Where to do that compute in memory, if I were to do compute in memory. Is it always good to do compute in memory? Probably not. It really depends on the workloads. So you have to look at, for example, the roofline plots and figure out, hey, do I, for example, is it compute bound or is it memory bound? In what way it is, and based on that, you can decide to do the compute in memory operations. And finally, at the end of it, and I also feel that the DRAM and the HBM stack, depending on how you do that, you can potentially do some of these compute in the DRAM with a logic die too, which we haven't talked about here. And at the end of it, if you have to really think about the technology and NVMs and other technology, there's a need to think about this entire stack, what we start calling system technology co-design. And if I do that, then potentially we can see the benefits compared to CMOS, if there is any benefit to any one of those technologies. So with that, this is actually moving really slow. So I'm going to stop here and try to see if I can answer any questions. Yes.
Question. Did you look at neuromorphic computing?
Neuromorphic computing. Yeah, neuromorphic computing is an interesting term. Everybody has their own kind of definitions of neuromorphic computing. A standard DNN could also be neuromorphic because it's weakly inspired by the brain. But yeah, some of the things that I just mentioned about spiking networks and all can be considered to be neuromorphic.
What is your vision for how it will be used in the future?
I feel that if I were to think about the main difference between an ANN and an SNN, if I were to now talk about ANN and SNNs, the main difference is that the membrane potential in an SNN stores a value. So I have a leaky integrated fire kind of neuron, and I store a value, meaning thereby I can remember the past. And with a leak, I can try to forget some of these things, right? Whereas in ANN, in order to do that, I need more layers. So depending on the kind of applications, you might say, hey, it can be a hybrid combination of the first layer to be a leaky integrated fire kind of neuron. All the later layers can potentially be, for example, an ANN, a standard ReLU activation. So depends on the kind of application. The kind of things that we looked at, in fact, it turns out one layer of, in some cases, one layer of leaky integrated fire neuron is good enough.
So you can have hybrid.
Yes.
So are there any questions about bitwise reproducibility? If you run the same program twice, you get the same answer or not?
You would get the same answer. You would get the same answer, but there's no stochasticity in here. But if I were to think about the neuron being stochastic, then you may not. You might have to run it a few times. Yeah.
You said that that the resistance drift of resistive RAM and PCM limits their ability to perform training. Can you explain why?
For the endurance part of it, I'm just talking. You have to be writing it too many times.
So it's not a drift.
So
but
no, what I was suggesting is that one can potentially do transfer learning. So you can have some of the layers to be in RRAM, right? And the rest can be in SRAMs. So you write only into the SRAM, so you back propagate up to the SRAM part of it, update it. But when it comes to forward propagation, you do it all the way from the inputs. Yeah.
So I've heard that one of the problems with spiking neural networks is that it's very hard to train them, or at least the standard backpropagation kind of training doesn't work for them. So if you're advocating using some sort of spiking networks, how did you do your training?
The training is a problem. Training is not easy. I mean, for example, you have to train it over time. So it's backpropagation in time that one has to do. Now, a few things that is kind of interesting is that, if I have one layer of the spiking layer, then training is easier.
Well, that's, yes. But I thought the big problem, the reason that people haven't really done very much spiking networks is because I thought.
One of the other things is that people were just taking an input and changing it to the time domain. For example, do Poisson rate coding. And I think that's very inefficient. Because if you take this input, analog input, and if you can spread it over time, right, that's very, very inefficient from training point of view. You can potentially think of, if you want to use a spiking network, right, first layer of the neural network can actually be the spike generator. So the analog input comes in, you do summation of VI times GI, and you generate the spikes. So in those cases, the training is still difficult because you have to now train it over time. It takes a longer time to do. Yeah. Training is still going to take longer time. Yes.
So, oh, okay. So let's say that I have a neural net where it all fits, the memory fits in one chip, okay? And now I have two options. I will do the best possible sizing of my memories and stuff like that. I would do as much parallelization as I can for a digital implementation, which is like compute right outside memory, right? I would have all these, small memory arrays, and then the competition is this computation inside memory arrays that you were talking about, analog computation. So
analog or digital could be.
No,
digital.
analog. Analog inside memory computing. I'm comparing against. Okay. So everything said and done, what do you think is the real benefit from an you can talk about EDP or whatever you like of this optimized digital implementation and this inside memory, not at a macro level and all that,
Yeah, one can certainly do an analysis of it. The main advantage of, if I were to really look at analog computing memory as opposed to digital computing memory, is going to be that the problem is going to be the ADC. And if I can't get rid of the ADC, I'm going to still have problems. So I have to have training in the loop to understand those quantizations. Otherwise, I may not get the benefits.
Okay, you do whatever the best you can, in this domain and that domain. Do you have a sense for what the real benefit would be?
And the real benefit is going to be then if I were able to everything. It depends on how far I have to go and fetch my memory.
No, that's why I said it. Everything fits
No,
on
but
chip. Yeah.
Sure, but I cannot have arbitrary numbers. I mean, if I
just
assume,
to take one example.
if I have any number that I have, if my memory cost getting stuff from the memory and then computing it is 0, then I don't have any
Well,
problems.
But the point is that in the analog computing, you have already assumed that all the data you need is in that memory.
Yeah, that's why,
You've already assumed that, because if it wasn't, you couldn't do the computing there.
Right,
So
in some ways. No, I am bringing in this thing too.
yeah.
I have to bring in some, depends on where I'm. If I'm doing in the register file, may not be large enough, right? I'm basically saying that you still have to have sort of a global memory in some ways that you've brought in data.
So let's say everything
depending
fits on
that.
chip. Just to be fair to both parties, right? Everything fits on chip, so that I don't have to worry about that external.
If
memory.
everything is there in every core that you have, you don't need anything, everything is there, then you can actually do complete their memory. It should be as good as anything else.
So then I do not see, if that's your answer, I guess this is
If
going to take a
everything
longer
fits in.
time. Then I do not see what is the benefit of inside memory computing, because if you have to bring something from somewhere,
The
then you
point
have to
is
bring in
that-
both places.
You have to bring in both places, no
So
question
then,
about it. But I think the thing that I'm talking about is that, you can do, even if it's an L1 cache or an L2 cache, right? The access times and those things can potentially come into picture.
But you,
If I were able to do that,
So, in principle, we have recess
Okay.
now, so you guys can for sure keep talking, but,
Maybe we should.
and everyone else can hang out in your corner.
We should have a special group.
All right, let's thank the speaker again, and in principle,